So this is the set of fellows of degree. So this is a span of psi. Charge is m, and the degree of psi is d. So degree, if you remember, was energy of psi minus energy of psi m. Okay, and we said the dimension of this is PD and so on. So dimension of FMD is the number of partitions. Okay, so all this from yesterday. So here's a nice little consequence of this. So we can try computing the following generating function. You run over all these psi's. So take all the basis vectors, semi-infinite monomials, and for each psi, let's calculate the following two quantities: q raised to the energy of psi, t raised to the charge of psi. So consider this generating function. Okay. So what this generating function does is to keep track of both these quantities, right? For each semi-infinite monomial, I note down what its energy was and I note down what its charge was, right? And now I have to run over all possible charges and all possible energies. So observe this generating function. So we've already said something about this generating function. Number one, if you organize it by charge, which means I first fix some charge m, which is in z. Okay, so look at t power m. So I fixed charge m, and now I need to only look at this portion here, right? So if I do that, then what do I get? Summation m in z t power m, and what's left here is summation over all psi of charge m. I need to only sum over guys of charge m, and it will become q to the energy of psi. But let me also do this. Let me add and subtract energy of psi m, and I'll put an energy of psi m outside. Now what is this? So what am I doing here? This is q to the, this was exactly the degree, right? This is how we define the degree, which is the energy relative to the ground state of that charge. So this is the degree of psi. So this is, I am now summing over all charge m fellows q to the degree psi, which is, since we know what the answer is, it's the number of partitions of D. Therefore this is nothing but summation over all m in z. It's q to the energy of psi m. If you remember, it was m into m plus 1 by 2, t to the m. And now this is just the generating function for partitions. So this is the generating function for the number of partitions of D, which we have already seen many times, is the product 1 minus q to the n. M greater than equal. It's fine. So that's the value of this generating function. Okay, it's fine. Now on the other hand, there's also another thing we can use to compute this. We after all know, so let's not organize it by charge in this manner. Let's just work directly with psi's, right? I know what any psi looks like. Every psi is actually these two pieces of information. Given a psi, there are finitely many positive integers associated to psi and finitely many non-positive integers associated to psi, right? Those are the electrons and the holes. Every psi is uniquely determined once I tell you what positive integers I am picking for the electrons and which ones for the holes, right? So now what I need to do, therefore, how do I find the energy? I know how to find the energy and this in terms of the mi's and the ni's. Okay, so what I'll do instead is, each psi is after all determined by this sequence of mi's and this sequence of ni's. So I will sum over all possible mi's and ni's. Okay, just take all possibilities for it and just do whatever it is, q to the energy, which is summation mi plus summation ni, t raised to the number of mi minus number of ni. So I'm just being slightly loose here. This is with respect to that notation there, that I've assumed there are p of the mi's and r of the ni's. Okay, so this is sum I equals 1 to p, this is sum I equals 1 to r, and this is p minus r. Okay, so now it's easier to think of it as follows. I choose some p distinct positive integers, right? So let me start out by saying this. How do I choose p distinct positive integers? If I didn't have t at all, what would I do, right? I would just choose choosing p distinct positive integers, the generating function is just this. This is the generating function for if q to the summation mi, where mi runs over all possible choices of distinct positive integers. But I also have to choose some negative integers, so some non-positive integers. So I'll say, well, meaning I have to choose some ni's, which are again, sorry, ni's are non-negative here. So this is k greater than or equal to 0, 1 plus q to the k. So maybe these are the ni's if you wish. So let's call these m's and n's. So these are like the mi's and these are like the ni's. Okay, so this is what I will get if I didn't have the t's there, because this corresponds to choosing so many distinct mi's and so many distinct ni's. But now, if you look at this, I also need to throw the t in. The t is the following: each electron gives me, it increases the charge by 1, and each hole I choose decreases the charge by 1. Okay, so when I also put the t's in, every time I choose an electron, it contributes a power of t, and every time I choose a hole, it contributes a t inverse. Okay, so this is in fact the generating function. Okay, so now here I have to run n from 0, m from 1. So maybe we will just run both. So write it as a single. Just run n from 0, but make this n plus 1. Okay, so these are the choices of electrons. When n goes from 0, this goes from 1 onwards, and these are the holes. When n is 0, this goes from 0 onwards, right? So what have we proved? We have proved that this guy here is equal to this guy here. Yes. Yes, it does. I have chosen that. See, n is now 0 for this term. The holes go from 0. Only the electrons go from 1. That's the n plus 1 there. I've added I just re-indexed so that I write it as a single index. So there's a difference. I've taken that into account. Okay. Now what identity is this? This sum divided by this product equals this product. What? It's a Jacobi triple product. Okay. So I can just take this guy over to the other side and write it as, so corollary we've just proved just by analyzing this generating function so this guy t to the m is the computation when you organize it by charge, and now I'll take this over to the other side, product n greater than or equal to 0, 1 minus q to the n plus 1, 1 plus tq to the n plus 1. I mean, this is one of the forms. This may look a little different from what you've seen with what Venkatesh did, but it's just a question of change of variable. It was probably q into m into m minus 1 by 2. So if you replace t by minus qt, I think you will probably have to also do a minus qt so as to get the m into m minus 1 by 2. So if you replace t by minus qt in this formula, it should give you the formula that Venkatesh has talked about. It's just a substitution. Okay. So anyway, this is just a sort of a little thing. So the key thing to keep in mind here is that every psi is really given by these two sets. This set and this set determines psi. So that was the key take home from this. Okay, so of course, why are we doing all this? I mentioned this at the very end yesterday, that the reason we want to do all this is because this is actually a representation of GL infinity. The fermionic Fock space admits an action by elements of infinite matrices. So how does an A in GL infinity act on the fermionic Fock space? In fact, it acts on each Fm. It leaves each Fm invariant. So we did this at the very end. The action is given as follows. It's just the usual action on like finite wedge products, the same action works. So this is Vi2. If you have this, it's like the derivative rule, which is it leaves everybody except one term fixed. Okay, so all wedges. So some V I k plus 1, it only acts on the V I k term, and this is V I k minus 1, blah blah blah, and this is now the sum over all possible k's, k greater than or equal to 0. So that's the only action, only on the kth term, and now you have to sum over all possible k's. And this was finite because the matrix was, it had finite support. The columns A, V, I, K would actually be 0 for all but finitely many of the V, I, Ks. Okay, and it left VM invariant, it left FM invariant. That's the other thing we checked, because knocking off the effect of applying an A on a VIK is like it replaces that VIK by some linear combination of other VIs, and replacing one VIK by some other VIs doesn't change the charge, because the charge is like we argue, you either change an electron, make it another electron, or if it was a if you make it into a hole, then you're simultaneously removing one electron and one hole, so still the charge doesn't change. Which one? Yeah. No. I mean, I just re-indexed it. Think of it like that. See, I wrote it as two separate products initially, right? So I'm saying this guy was, so the way I wrote it was this. I said this is TQM, M greater than equal to 1. And then this was another product, N greater. So yeah, instead of multiplying all of them together at once and all of them together at once, I'm just, it's still running over the same set. I've just re-indexed, that's all. So I'm saying,
I think this will be an infinite product.
This is an infinite product, yes. Everything is, but they're all formal infinite products. I mean, there is no convergence. I'm not thinking of it as numbers. See, here it's in the formal power series ring generated by T and Q, if you wish. Yeah? Okay, so by the way, this was suggested by Digjoy that I should tell you about this. Okay, so I have this action here. The point is, this action is well defined, but the thing I was about to say at the very end last time is that in fact this action is well defined even if A comes from A infinity, A bar infinity, almost. So if you take matrices which are supported on finitely many diagonals, as long as those diagonals are not the main diagonals, you're still okay. So let me mention this point. So remember, A bar infinity, those matrices supported on finitely many diagonals. So let's pick A in A infinity of a certain form. Okay, so A, let's say, is supported on some non-principal diagonal. So there's this principal diagonal here, which I don't want. So let me take A supported on some other non-principal diagonal. Okay, so it has some non-zero entries. So what do I mean by that? So A is like this with Aij non-zero, 0 except for I minus j equals some k which is not 0. So on the kth diagonal. Okay, so I fix k not 0, and just, okay, now let me say it like that. Fine. So this is a matrix which is supported on the kth diagonal. K is not 0. Now observe that still this formula works. A acting on psi, I claim, will still only have finitely many contributions, because what is this? I'm supposed to act A on each term of this, each of the VIs, but what does the action of A do? because it acts, it's supported on the ith diagonal. Observe that A acting on any Vj will give me some element, will give me some multiple of V, what is it, I equals j plus k, right? It gives me Vj plus k. This is some multiple, some scalar times Vj plus k. This is what A does. It takes each Vj and maps it to some Vj plus k. Fine, k is not 0. In other words, so don't worry about the scalar right now. So it's some scalar, but what it's really doing is like a shift operator. It's taking each Vj and sending it to Vj plus k. It is shifting it by some amount. It's either if k is positive, it's shifting it to some j plus k, or it's sending it to j minus k. But if you look at this, the action of A on this sort of infinite wedge product, observe that this wedge product has the following property, that beyond some point to the left, all the negative integers appear. Right? Every single negative integer appears without a gap. So now when A acts on those terms, okay, when say I have all negative integers, let's say until say everything minus 10 and below appears, for example, and let's say that shift k is say 3. That means each Vi is being sent to Vi plus 3, for example. The point is, this, if you look at far enough to the left, A acting on those guys will just map it to something which is already there in the list. So for example, as I said, if psi looks like ... V minus 8, V minus 9, V minus 10, and then maybe it's something else. It doesn't go in sequence. Until here it's completely in sequence. Then observe that if k is 3, everything is only going to get shifted by 3. So for example, when A acts on this term, V minus 7, it will map it to some multiple of V minus 10. Okay, but V minus 10 is already there in the list. So we had this thing which said that if any two things in the wedge are two equal things.
Say V minus 12, V minus 11, V minus
I'm sorry, in the other order. Indeed.
that's V minus 10.
Okay, keep this at 10 and then minus 11, minus 12. Indeed. Sorry.
So if you have V minus 13, then
V minus 13 would map to V minus 10. Thank you. So V minus 13 would map to V minus 10, which is already there. Okay, this wedge has this thing, and when you have two equal things, it's 0. So V minus 13, minus 14, and so on, a shift of 3 will produce a vector which is already in the list, and therefore it will give you a 0. Okay, so it's becoming 0 by virtue of the wedge, that there is another repeated guy, not by virtue of, here it's for more trivial reasons. It is 0 because it's actually 0. Okay, that, I mean, A Vj itself is 0. Fine, this is okay? This is why you need fermionic. You need wedges for this to make sense. Absolutely. But this is still going to fail if your thing is supported on the main diagonal. Okay. So if you have, for example, we saw last time, the identity operator wouldn't be able to act on infinite wedges because it will give you infinitely many non-zero contributions. Okay. So observe that if k is 0, in other words, so let's take that case. Suppose A is just Aij with Aij 0 except on the main diagonal, Aij 0 except on the main diagonal. Okay, so it's Ai's, it's a diagonal matrix with some entries. Then observe that A acting on that guy would give you the sum of all the Ai's, right? So if you try to make A act on that wedge, what will give you, will just give you summation A, AI naught I naught plus AI1 plus AI2 and so on. So this is what will give me all those diagonal entries. Correct? That's what it will give me if I actually tried to make it act, and of course that's not defined because it's an infinite sum. Okay? So what we do now is the following. We modify the definition of the action. Okay. So this action won't work. So I'm going to modify the action. Modify. Here's a modified action of such matrices. The principal diagonal guys. A modified action of A on psi or on F, whatever, is defined as follows. We say the following. It's given by, it's determined by the following thing. Let me tell you how the EII acts. Okay, just the diagonal matrix with an 1 in the ith place. So we'll say the following. EII acts on psi as follows. It either gives me the actual action itself, EII psi. So or just the operator EII acts. Okay, EII acts on psi as follows. It gives me just the actual answer if I is greater than strictly positive, but it gives me EII minus identity acting on psi. In other words, it gives me EII psi minus psi if I is less than equal to 0. So here's a modified action. So I don't know, we should probably say that it is modified in some way. What should I do? So anyway, I mean, let's put a dot here.
What is EII psi on the right side?
Sorry, what? EII psi, this EII psi is the usual EII psi. So this is my new EII psi. EII psi is just given by this. It will give me just the ith, it will give me just 1 times, it will give me psi. EII on psi, it will give me psi if that I occurs in psi. See, if at least one of the IKs is equal to I, then it will give me psi. So, I mean, let's just do it by example. So, if psi is, say, psi naught, the string of guys which ends at 0, then how does EII, just the usual action of EII on psi. By definition, it will pull out. So what will it do, right? That's the action. It will act term by term. EII acting on any VI will give you back VI provided that's, I mean, it will give you back VI for I, but all other VJs will be killed. Okay. So EII, so observe how to figure out EII on psi. This is the usual action, by the way. This is a modified action. To find usual action, all we need to remember is the following. How does EII act on the basis vectors? This is if k equals I, this is otherwise. Right? EII kills all but VI. Therefore, when it acts on psi, which is a wedge of the V's, it will give you 1 if VI occurs in this list, okay, among the wedges. And if VI does not occur in the list of wedges, then it will give you 0. So observe therefore that EII acting on a psi like this will either give you psi or 0, depending on whether that, if some ik equals I, then it will give you psi, and if none of the ik's equals I, then it will give you 0. Yeah? So that's the action. All I have done is just unravel the action on the wedge. So this is the usual action of EII, okay? But now I have a modified action. So I'm changing it to this. I'm saying EII will act like that provided I is positive, and if I is negative, then it acts in this way. Fine? So we have modified it for whatever reason. So let's just see what it gives us. Okay, so first, how does it act? Therefore, how does a typical element A act? So let's now go back to this thing that I wrote out. When an element A, which is supported only on the main diagonal, when an element like that acts, this is the original action which is not defined. Let's at least see if this fixes this anomaly. So I'm now going to ask, how does the modified action of A work on this semi-infinite wedge? Okay. So what will the modified action do? So this is the action. So what is it going to do now? What's the answer? So A looks like that. So A is just the diagonal matrix with AII. So maybe it's easier to just say A is just the diagonal matrix with entries called AIIs. Okay, maybe let's just call it AI even. Why bother with AII? So let's say it's a diagonal matrix whose entries are just called AIs. So there's A0, A1, A2. So how does this act on this? Okay. So we have to take both cases separately, right? So so this is how a single EII acts. Okay. So my A now is a linear combination of the EIIs. This is what my A matrix is, right? So I'll figure out how each EII acts. The positive EIIs, how will they act? Yeah. So if I naught is sorry, how should we do this? Right. Okay. So let me split this. Let me say this is over all I in Z. It's AI, EII. This is the definition of A acting on psi. Okay. Now what's that? Let me split it again into two pieces. If I is positive, the action is defined one way, and if it's negative, it's a different action. Only if it makes sense. So which one? AI, EII is okay. That is fine. I mean, that is just another name for this matrix, if you wish. So don't think of it as that's just that diagonal matrix. I'm just calling it this. That's all. Yeah.
It's just a name.
Just a name, if you wish. Yeah. I mean, the action is finally defined by actual left multiplication on the vectors, right, or on the wedges, on each component. Okay, so I positive. So how does EII act on psi? It will give you back psi if I occurs in psi. Correct? So this will give me back psi for each time I occurs in psi. Okay, so this is the sum of AI times psi, but the sum is only over all positive I which occur in psi. Okay, you're already great. Those are the electrons of psi. Okay, plus the sum I less than equal to 0. What will we get here? If you sort of see, it is AI times EII coaction on psi, right? Now how does EII act on psi? Again, if I occurs among this list here, then EII psi will equal psi. If I occurs, this is psi, and if I doesn't occur, it is 0. Okay, but then I am subtracting off a psi. So what will it do now? If I occurs, this is 0 because I have removed the psi, and if I doesn't occur, it gives me a minus psi. Okay, so this is now going to give me a minus sum over all I psi such that I does not occur. This is fine. So this modified action therefore is well defined. Why? Because the set of electrons and the set of holes are both finite. Right? This is how we define psis. They are the ones which have exactly finitely many positive i's which occur and finitely many non-positive i's which do not occur. Okay? So this is just the sum of AI. I is an electron of psi minus the sum of those diagonal entries AI such that I is a whole of psi acting on psi. So it gives me that multiple of psi. Okay. In particular, what does the identity operator give you? No. Charge. So the identity operator, which is not defined, the old action is not defined. Now the new action is exactly the charge, and what gives you the energy? So observe the identity operator, which is the diagonal entry.
Oh, this is the sum of one.
So all ones. This is along the main diagonal. So that guy, now the new action of that on psi You notice what we have just done, it's just the charge of psi.
For energy, you need to put I, A, I to the I.
Take this diagonal matrix, AII equals I, 0, 1, 2, 3, minus 1, minus 2, minus 3. Look at this diagonal matrix. When this diagonal matrix acts on psi, it's exactly the energy. This is, yeah, minus infinity is on the top, yes. So my negatives are, so 0, minus 1, minus 2, etc., 1, 2, 3. It's fine. Yeah, sorry, I should have said, my rows and columns are always like that. Zeros bang in the middle and then I go up and down. So this is the energy, because now this will give me the sum of the AIs minus sum of the electrons minus sum of the holes, the actual numbers which occur. Fine. So those are those two operators, right? So now, at least with this modified action, what we have remedied is this anomaly that there is this infinite sum. Now we don't really have infinite sums anymore, because we have also restricted our semi-infinite wedges to be of a certain kind, right? They must lie in the fermionic Fock space, which means they must have finitely many electrons and finitely many holes.
We have to check that it's a real.
Okay, great. So of course, I silently said all this, but you are not at liberty to just happily change actions in this way, right? Because the action on the wedge product, the usual action is an action by usual properties of wedges, but if you suddenly change something like this, it's not clear anymore that you have a Lie algebra action. Okay, and turns out it's not. Okay, it turns out it's not a Lie algebra action. Okay. So what is it that you need to do in order to check that something is a Lie algebra action? So I have this Lie algebra A infinity. This now acts via this new action. So by the way, I only said how the diagonal guys act. I didn't say how the other off-diagonal fellows act. They act in the usual way. You can just, as we already saw, there's no problem with those, right? So this is only the new action is only for the one supported on the main diagonal. The other diagonals are okay. Okay, so action. So if A is supported on I don't know what to say, not on the principal diagonal, on other diagonals, then keep the same action. So then keep same old action. You only redefine it here. Okay. So it's almost the old action. It's all, for almost everything it's the same. It's only for those fellows which are supported on the main diagonal that you're tweaking the action. So this new action on the fermionic Fock space F is not an action. So how do we check that this is an action? You're supposed to take two elements of A bar infinity. So for example, you pick, okay, so let's say, how do we check that something is an action? You take two elements of A bar infinity, meaning you take two infinite matrices supported on finitely many diagonals, and then you compute their action. So I should maybe give this a name just for, so let's call this map phi, this action phi. In other words, when I think of it as an endomorphism, so what is phi? It's a map from A bar infinity. I think of each. So this is the operator which tells you what the action is. Okay, I'm just giving the action a name. So I need to check the following. If I take the bracket of two elements of A bar infinity, and so here the bracket is the usual AB minus BA, and then I see how that acts, then that answer should be the same as the action of phi x and phi y. Right? This is what being an action means. Okay, and in this case, if you notice, where are you likely to find problems? So let's only take the EIJs. Okay, so I just take EIJ, EKLs. Let's start with just the basis, these guys. So I try to see if this and this match. And you sort of have to check it for all the cases, meaning the case when one of them is diagonal, when I equals j, and when all of them are off diagonal and so on. It turns out and I will not do the computation here, maybe in the tutorial, it turns out that this is true for most of the cases, as because the actions are the old actions most cases. The case which is problematic is really when you have the bracket of two things giving you an answer which is diagonal. Okay, I have two off diagonal things, say Eij and Eji, then if you see their bracket is now something that's supported on the diagonal. Okay, it's this is of course Eii minus Ejj. So this is the case which ends up giving you a problem. You don't quite get the thing on the right hand side, but what you get is just a deformation, is just a slight change. This is the identity operator on F. Okay, it turns out that what you get is off from this by a 2 cocycle. Okay, so this is just alpha xy, but the general answer is this. Turns out that there is a function alpha such that phi of xy is this plus alpha xy times the identity operator, just off by a 2 cocycle, where alpha is a certain 2 cocycle. So alpha now is a 2 cocycle. So you've seen this 2 cocycles in Venkatesh's talk. So 2 cocycle of a bar infinity. In other words, it's a map from a bar infinity cross a bar infinity to the complex numbers, satisfying some properties. So in this case, I will just tell you what the thing looks like. Eij, Ej is really the only problematic case where there is a 1. Eij, this is if I is a hole and j is an electron. This is more or less the only. That's the only non-zero case, and it's 0 for all other pairs. Okay, let me check that I'm not telling you something wrong. If I is less than equal to 0 and j is greater than, yeah, absolutely, and 0 everywhere else, and 0 for other pairs, and alpha or dot is 0 for all other pairs of Eij, Ekls for all other pairs. Okay, so this particular function then extended bilinearly turns out to be a 2 cocycle, satisfies all the properties. So what does that mean? It says that this is not quite an action of the Lie algebra a bar infinity. It's what's called a projective action. It's off by a certain scalar, or in order to make it a proper linear action, you have to construct the central extension of a bar infinity. So this 2 cocycle, just like you have seen in the case of the affine algebras, now what we do next is to say the right object, this suggests that the right object to study is not a bar infinity, but a certain central extension of a bar infinity. We extend it by adding a central element C, just like we did in the case of the affine algebras, constructing it from the loop algebras, where via this cocycle alpha. Okay, so the new bracket is given any xy, the bracket in a infinity, it will just be, should have been some funky looking a. This is the usual bracket as elements of a bar infinity plus alpha xy times c. Okay, where alpha is given by this. This is the function. Okay, so you centrally extend it, you get a new Lie algebra. Huh. Right. Huh. You are asking whether it's a unique, whether it's a universal central extension. I don't know the answer. Possibly. Yeah, I have to look that up. But at any rate, in some sense, we have gotten to this by our analysis of the the action, trying to make this act on the fermionic Fock space. Okay. So now the point is, having done this, what we obtain, therefore, this new action is an honest action of this new algebra. So now conclusion of all this analysis is that while a bar infinity doesn't admit an action, a infinity admits an action on F. on the fermionic Fock space. Okay, and how is the action defined? If I take an element x which comes from the a bar infinity portion, I just make x act by that operator phi x. Okay, however it acted, that modified action. In other words, off diagonal elements will act as usual on the Fock space. The main diagonal elements will act by this modified action. Okay, the I negative and positive will act differently, and we still need to say how C acts. So how should we make C act?
C will act by identity.
By identity. So notice that there is no C here. What does this formula here say? It is this bracket plus alpha xy times the identity operator on F. Right? So in order to make this an action of the centrally extended algebra, I need to make the center here act as identity. Okay, so you make C act as I, you make the remaining fellows act as phi x, and now this is now a well-defined action, an honest linear action of this Lie algebra, not a projective action like in the earlier case. Okay, so this is a well-defined action. Sorry, what? C should act as minus identity. Why? Let's check. Bracket of xy. So this is now the new bracket, which is the old bracket plus this, right? So now if I see how, so what is it? So to check that this guy is an action, let me apply, so this is my new map. So let's call this phi tilde. Okay. So what is phi tilde? On x it is phi, on C it is identity. So I apply phi tilde to both sides. So phi tilde of this guy is just phi tilde of this element plus alpha xy times phi tilde of this element. That's what I have to check. Sorry, that's what I know. But phi tilde of this is phi of this, which is phi x, phi y. Aha, I'm off by a negative sign.
That's right, because then that has to cancel out with that.
That will have to cancel this? No, then I must, let me check card center right now. So.
Or maybe if you change the sign of alpha, then
Right.
which is that one.
No, I just want to ensure that I didn't write this wrong. So phi x, sorry. So I wrote that wrong. It's phi x, phi y equals this. Yeah. So it is actually the other way around. So in fact, it's minus alpha. Sorry. Absolutely. Thank you. Yeah, I wrote in the wrong order. Okay. So anyway, I mean, we should check this during the tutorial. So it's a nice thing to check. Yes. Anything value of alpha is correct. So I want this to be my alpha. Absolutely. Okay. So now is it okay? Now if I centrally extend it as plus alpha xy, then everything works out already. Okay. So I get a representation of A infinity on F. Now let me say something about these representations. I'm sorry, what? The what? I see. Yes, you're right.
Almost trace to the except the negative stays JI.
Correct. No, except there it is not, it's k times, no? See there, in the case of the affine algebra, you mean? See, in the affine algebra, you will have that tensor t power k as well. And it will be k times k delta k minus L times trace of xy. No, but there is a k there, right? Correct, comma 0, trace of whatever, the AB. No, but that minus sign will come from the k in front, right? Because when you swap the order and you have the delta m plus n 0, the m and n are negatives. Sorry. The m will become a minus m when you swap the order. But here in some sense that's not there. But I mean we'll eventually come to that bit that we'll embed the affine inside this. So this central extension is going to become, it's not just some random thing that comes up right now. We will soon see that you can embed the loop algebra inside a bar infinity, and this central extension of a bar infinity will correctly match up with the formula for the central extension of the loop algebra. So we'll embed the affine algebra inside a infinity as a consequence. Okay, so that's coming next. But let me at this point just tell you what these representations are. So if you take this representation Fm, so the other thing again which is very easy to check, because the action is essentially the action on the Fock space of GL infinity, right? It is almost the same formula except in the diagonal case, but that still doesn't affect the charge. So it happens, so here are various facts or proposition. So number one, so I already said this, that if you take just the smaller Lie algebra GL infinity, then of course it keeps each Fm invariant, right? It acts on each Fm. That's one thing we have seen. But now we have a new action of A infinity. So A infinity also preserves each Fm. Okay, by this I mean the action on the full Fock space F is such that each charged piece is preserved, each Fm is preserved. Why? Because let's look at the action. If I take an off diagonal guy, that action was the same as the old action of GL infinity, essentially, extended to the infinite case. That preserved charges, and the new action is only kicks in when you take the diagonal elements, and the new action is just, what does it do? It gives you the sum of the electron values, AIs on the electrons minus AIs on the holes, times the original psi. So psi was in Fm, it just gives you some multiple of psi. So it's still in Fm, right? And C, of course, is just acting as identity, right? So this new action that we have defined still preserves the charge. It cannot change the charge, right? Diagonal elements still act as scalars. They multiply each psi by some number. So this is the case. Now, what sort of action? So it's an irreducible representation. Okay, and the same thing is true here. Okay, so this is an irreducible representation of GL infinity. This is an irreducible representation of A infinity. Okay, so I'll just say a few things about the proof. A infinity itself, yeah. So let's start with GL infinity. So the first thing to observe is that, see, what was Fm? Fm was, sort of, there was this vacuum vector psi m inside Fm, the charged vacuum, which we said everything else is obtained, everything else of Fm is obtained by finite excitations of psi m, right? That was how we wanted to conceptualize it. Now observe, this just means the following, that any other element psi of Fm can actually be obtained as follows. You start with your psi m, okay, and then what do? You take some electron and you push it up to some larger point, right? You don't do anything to any of the others. Now what is that action really? What are you doing? Suppose I take an electron which lives in the 5th energy level and move it to the 6th energy level. Absolutely. That's all I'm doing. So imagine that move is just some Eij. Right? I'm applying that current J. J is the current value of the electron. I is the new value to which I'm moving it. Okay. Now having moved the first electron, I then take up the second guy. I want to move it to some other location. It's some other action of Eij. Psi m was the charged vacuum, which is it's everybody Vm and downwards. Right? And other guys in Fm are just obtained by taking this Vm to some place, m minus 1 to some place, m minus 2 to some place, and so on. So finitely many of them are moved. So this finite moves that we are carrying out really is like acting a sequence of Ei, some finite sequence of Eis. Fine? So what that says is that every psi can be obtained from psi m by the action of repeated action of elements of GL infinity. Okay? So this just means if you take the universal enveloping algebra of GL infinity and act it on psi m, you will get everything in Fm. Okay? So this just means repeated actions of the Eijs. And so this in particular means that this is an indecomposable representation of, I mean there's a little bit more, that there is some grading as well. So claim is this is an indecomposable representation of GL infinity.
Just because you can.
No, I mean there's a little bit more, like I said. So that's the grading, which is, see, okay, how do we prove? So let's prove that this is an indecomposable representation. You can't. No, not always. Indecomposable plus something else will give you irreducible. That's what we will eventually get to, correct. No. What do you mean highest weight? That's the grading. That's what you mean. See, the point is there is some additional structure here, which is the grading. There's an energy grading of Fm, right? Recall, psi m is, I don't know, psi m is the lowest energy, I suppose. Psi m is the ground state, right? It's a guy of lowest energy or lowest degree. Then there are degree 1, degree 2, degree 3, and other fellows, right? Now the point is, you can do the following. If you have, I don't know, is that required? No, okay. So my claim is that psi m will belong to any module. If I have a submodule, then I can make psi m belong to it, right? That doesn't require anything much, no? If it's a linear probably I need some grading, correct. If it's a linear combination of the psis, so you take some element of the submodule, and then you just try to reach psi by acting, by the opposite things, by the Ejis. Correct. If you have a linear combination, then you need to be slightly more careful. If you just had a basis element psi, you can get to psi m. If you had a linear combination, if they lived in the same grade, right? So if I lived in the same grade, it's a graded space. So the point is I can reach psi m. Sorry, how do I argue this? If I have, it's a cyclic module is fine.
But
that doesn't imply. So I just want to show that you can. Each different grades is okay. If I can just start with the lowest grade guy or the highest grade guy and get down to psi m, right? But what if my linear combination all lived in the same grade? If you are in the same grade, then you need to do something a little bit more. Okay, sorry, I have to think about this a little bit more, but maybe by the time of the tutorial. So the point is, so there are two things that we need to say about this. Number one, it's indecomposable. Okay, that should somehow follow from this grading and the fact that it is a cyclic vector. And number two, that this is unitary, in the sense that there is a certain inner product on this space, which is sort of contravariant for the action of GL infinity. Okay, so there are these two adjectives which will together tell you. There is an operator which gives you energy, yes. No, the energy operator lives in A infinity, not in GL infinity. Yeah. Why? Correct. Right, that's this grading, that's energy grading. But then how does that still, huh? Yeah.
It's a sum of.
I see. Same as Vermont. Okay. That's all we need even here then.
Sorry, so each
See that
submodule will be a sum of its intersection with the.
Each submodule will be graded. That's the point. See, each submodule is graded. That's the thing you need. Right. See, weight module, what do you mean by weight module in this case? So that's what I'm saying. There's an operator which determines the grading. Correct. But then it has to be, right. So it's just a grading of the module. Yeah. No, the smallest one is one dimensional, etc. is true in this case, because of the way the energy was defined, right? We have an energy grading. Okay, so it looks like that's the sort of thing we should do.
Sorry,
right?
What if the smallest one is one dimensional?
Then like in Verma module, so if a submodule is graded, meaning if you write this as a direct sum of two pieces, those two pieces should have some intersection here. They will give you a direct sum of each graded level into two pieces, of each energy level into two pieces. But then the lowest guy is one dimensional, so the psi m will belong to one or the other, and therefore it will be the whole thing. Okay, so anyway, let's do it in the tutorial. So indecomposable plus this additional thing that there is an inner product on this space. It's unitary. This together implies it's irreducible. Okay, so there's a little bit more here, which let me not get into that now. I'm sorry, what? Yeah, so indecomposable, therefore irreducible. Okay, so that's for GL infinity. Now for A infinity, so let me say what the argument is to show it.
This was for A infinity.
No, this is for GL infinity.
Then how did you get the grade? I thought the energy and the equal.
No, the energy operator is in E infinity, but see that energy grading is anyway there. No, there is a grading by.
Yeah, but why should an invariant subspace?
We respect the grading.
Unless you have that
Have the operator. No, I understand. There's still something to worry about here. Yeah. Okay. Now, so maybe like you say, that argument will work to show this in the case of A infinity, I suppose. But I want to give you another argument, because I will also eventually need to show that this is invariant under the affine algebra embedded inside A infinity. Okay. So eventually I'm also going to say I can embed all the affine algebras inside A infinity, and this will continue to be irreducible even after you restrict it to the affine algebras. So there's something even stronger that we need, and to show that we will construct sort of another thing. So recall these shift operators. There is actually an even smaller subalgebra of A infinity under which the FMs are irreducible. It's not just irreducible for A infinity. There is a further subalgebra. So recall the shift operators. So recall I defined these things called lambda k's, which is just the diagonal matrix with ones only on the kth diagonal. So the shift operators were, when they were elements of A bar infinity, because of course they are supported on a single diagonal all once. But the point is, if you recall, we did the commutator of the shift operators, lambda k lambda L would just give you lambda k plus L, their composition. Therefore the commutator was 0. But the commutator is 0 in when you think of them as elements of k plus L, I'm sorry, as elements of A bar infinity, right? Because they commute in A bar infinity. But now I'm going to look at A infinity. So recall, now this is a central extension. So we have actually done something more. The bracket has changed. So what will this answer be? This is a 0 already, so we don't need to worry about this. So we just need to figure out what's the two co-cycle evaluated on this pair, right? When you have the two shift operators. Okay, so that's a computation one must do, and hopefully we will do that in the tutorial as well. And the answer, let me tell you the answer alone. It turns out to be k times. So this is the answer. It gives you k times delta k minus L. So k and L are these two guys. This is for all k and L in Z. Okay. So what does that make it? So let's look at these. Therefore, consider this subalgebra of A infinity, which is just the complex span of all these shift operators along with the central element, comma C. Okay. So firstly, this is a Lie algebra because the brackets of any two of them just give you some possibly mostly 0, but sometimes non-zero multiple of C. What? Yes, sorry, SLN hat in general. SLN hat, yes, I don't mean all the affines. Yes, you're right. Affine SLN. In fact, more to be correct, GLN hat is what we will embed inside this. Absolutely. So this is exactly what we call a Heisenberg Lie algebra, right? Venkatesh talked about Heisenberg Lie algebras and so on, I suppose. Okay. So a Heisenberg Lie algebra is exactly, this is, if you don't know what it is, this is exactly what it is. It's a Lie algebra with basis some lambda k in Z, the central element with Lie bracket given by every pair is k times delta k minus L. C and C is central. So Lie algebra with this set of Lie brackets is called a Heisenberg Lie algebra, an infinite Heisenberg Lie algebra. So you also have finite variants. This is a Heisenberg Lie algebra. Okay. So inside this there is a Heisenberg Lie algebra. Now I claim that these FMs are in fact irreducible for the action of the Heisenberg Lie algebra. So there is H that's sitting inside A infinity. Okay, H itself acts irreducibly. So this is GL infinity acts irreducibly on FM. H acts irreducibility on FM. Okay, and why is this? So if you ask, how do the lambda k's act? What do they do to an element psi, for example? They shift. What do they do to the energy of something? So I have psi, for example, and I act a shift operator lambda k on it. Let's say k is not 0. What does it give you? What does it do to the energy? charge doesn't change, remember. The entire A infinity will act on Fm. But if I take lambda k and make it act on psi, by definition, what will it do? It's lambda k acting on each component of the wedge, right? Wedge. One term alone, you act lambda k on it. Now, how does lambda k act on any given Vi? It shifts it by k. It sends it to Vi plus k. It's what? The energy of the new guy. What's the energy of the new guy? That's all I'm asking. If I take lambda k, act it on psi, what's the energy of the new fellow relative to the energy of the old guy? K times the energy of psi. What do you mean? See, what does it do? It just shifts each Vi by k, right? See, how does lambda k act? Psi is here, wedge. There's some Vi somewhere in the middle. This will just act on that term, no? Charge, right, but charge, remember, is the number of electrons minus the number of holes. It's a number of positive integers which appear among the ij's minus the number of non-positive integers which are missing. That's the definition of charge. So the point is, what could you have done? You could have taken a positive integer which appears and made it some other positive integer when you act by. Sure. Right. Yeah. It can push things down. Is that what you are worried about? Everything is? Everything is not pushed up simultaneously. Not simultaneously, one at a time, because that's the action, right? It's only one term at a time. Yes.
Always trips up.
Right. That would, I mean, that's also important. That's the GL infinity action if you wish. And that's important because that will help you go across charges. Because you will start with just the vacuum, the guy with zero charge, and you'll be able to also change charges. That's the cross. Okay. So here it's only changing one guy at a time. So lambda k Vi, what is lambda k going to do? It will map it to Vi plus k. I minus k. Okay, I'm always Vi minus k, absolutely. It's a kth diagonal, yes. So which means it decreases what does it do? Lambda k acts on Vi. So like he correctly says, it is Vi minus k. So what has it done? It's taken an electron living at the ith guy and moved it to I minus k. What has it done to the energy? That's all, right? Just reduce the energy by k. Right? So that's basically all it does. So the lambda case, so the positive lambda case will decrease energy by k, the other guys will increase it by k. Right? The negative lambda case will increase it by k. Fine? So the negative lambda case will increase the energy by k.
These are the same as Vienno's U and D operator.
Which ones?
Vienno is U and
U and D is just a finite Heisenberg. That's only two guys. See, this is the infinite Heisenberg in the sense Vienno's U and D will only be lambda 1, lambda minus 1 and C.
Exactly.
Those three would be this, yes. But this is not the infinite Heisenberg. You also have lambda 2, lambda minus 2 and so on. This is like adding 2 boxes, 3 boxes.
What do they do to partitions? They add.
What do they do? Good question. I don't know.
They add horizontal.
I don't know. One should analyze all of these. See, the point is this is not at the level. Oh, I see. You're saying it will be a linear combination, right? In general. See, it's not going to be a.
You're adding a hook, I think, because you're taking something and jumping only if that space is vacant.
Correct. But then it's a linear combination, nevertheless.
Still, that's how they are defined anyway, right? So.
Those operators. Acha.
Adding hooks and removing.
I see what you mean. Okay.
Yeah,
Correct.
no,
Adding rim hooks, that's what it is. Correct. You're adding rim hooks because that's what, I mean, this is the abacus. See, this is just the abacus because it's all distinct integers, but the partition is the undistinctified version, whatever. You add n minus 1, etc. Right. So you add a rim hook, that's what's happening. Correct.
Then this implies that adding and removing rim hooks also
Satisfy the Heisenberg relation. Correct. But with the 2. With the 2, coefficient 2 in front. That ud minus du is for k equals 1, that will give you a 1. This should give you a 2. Yeah, but good point, that will probably work also.
k.
K is 2, right? Lambda 2 and lambda minus 2 are what you're looking at.
Lambda k and lambda.
In general,
K.
with k in general. Yeah, yeah. K rim hook in your case, correct. Yeah. Yeah, sure. Yeah, it could kill it, yeah. I suppose, right? Because it will decrease the energy after all by k, and you can't decrease it beyond a point. But lambda minus k's will probably not. What is psi? Psi is a thing like this. Psi is just an element of Fm.
The
Basis vector, yes. Pure state, yeah. Yeah. What? No, but it acts one term at a time. See, it is the action is all wedges, one term alone is impacted, plus you impact a different term and so on. Right? So okay. So my point now is that, see, this is what it does. So now come the final proof of irreducibility depends on something about the Heisenberg algebra, which is if you have, so what's the picture? I have something at energy, so psi m, which is the ground state. Okay, so psi m has the ground state energy, whatever, m into m plus 1 by 2. C, sorry, I should have also looked at C and, so what is C on psi m is psi m because C acts as identity. But what's interesting is what's lambda 0 acting on psi m. What is lambda 0? No, lambda k is a kth shift operator. 1's on the kth diagonal.
Lambda 0 is the identity matrix, but the action.
Charge. We just said that, right? The identity matrix is the charge operator, gives you the charge. Right? That's a new action, remember. So the identity will act as m on psi m. It will just give you the charge. So now, so what's this general Heisenberg business? So what this says is, when I have my ground state, then when I keep acting by my negative Heisenberg modes, these lambda minus 1, lambda minus 2 and so on, it increases the energy by the appropriate factor k. Okay. Now there is this general theorem about how representations of Heisenberg Lie algebras can look. Okay. So there is sort of this standard, what's called the Fock space again. That's called sometimes the bosonic Fock space as opposed to the fermionic Fock space. So this bosonic Fock space just means there's this standard irreducible representation of the Heisenberg algebra, which looks like this. You start with this vector psi m. I mean, I'm more accustomed to drawing it from the top. So this is psi m, and then you just keep acting on it by, so this is lambda minus 1 psi m. That will have energy one more than this, and then so in the next level there will be lambda minus 2. Sorry. So in energy 1 more than this, there's lambda minus 1 psi m, and then in energy 2 more than this, there's either lambda minus 2 psi m or lambda minus 1 square psi m. Then in the next energy there will be 3 guys, lambda minus 3 psi m, minus 2 minus 1, lambda minus 1 cubed. Okay, and so on. So what are we doing? We're just acting by the negative modes. The point is these negative modes all mutually commute, because the only commutation relation is between a certain mode and its negative. So K and L have to be opposite signs for you to get a non-zero commutator. So if you take only the negative modes, they all commute with each other. They form a commutative subalgebra. So this guy here is just a model for, this is isomorphic to what's called the symmetric algebra of the negative portion of the Heisenberg algebra. So this negative portion is just all lambda k's, lambda minus k, k greater than equal to 1. So just take all the negative modes and take the polynomial algebra generated by them, meaning just all these possibilities, lambda minus 1, think of them as commuting variables, commuting operators, just keep acting them in this way. Okay. This is called a bosonic Fock space. This is the sort of the standard irreducible representation of the Heisenberg algebra. This is irreducible. Any irreducible representation is sort of isomorphic to this. There is really only one irreducible representation possible. And if you have sort of seen quantum mechanics and so on, this is, the Heisenberg algebra is like you have the position and momentum. Position and momentum are Heisenberg, right? But that's sort of finite Heisenberg, I suppose. No, I mean when you have right, in the finite Heisenberg case, so they always say that you can realize the position operator as multiplication by x and the momentum operator as the derivative operator, right? So this is supposed to be the standard realization of these two operators, and it will act on a space of polynomials in x in one variable. Okay, so this commutation relation, this while commutation relation, whatever it's called, is realized by that, the multiplication by x and the derivative. And if you have, this is more the infinite Heisenberg, you have many more guys. So what you have to do is think of it as a polynomial algebra and many variables, in infinitely many variables, and each operator will act, this guy will act as multiplication by its corresponding variable, and the lambda plus 1 will act as the derivative by that variable, by the partial derivative by that variable. Okay. So this is, I mean, these are all various ways of describing the same thing, but there is like the symmetric algebra, this is the mathematical formulation. You take the symmetric algebra of H minus, that guy is the bosonic Fock space. There is a way to make the entire Heisenberg algebra act on it. The negative modes will act just by multiplication. This is a polynomial algebra. The positive modes will act as certain derivations of this algebra, okay, certain partial derivatives. Now the point about this is there is really only one model possible. There is only one available representation, and the nice thing is that you can already see what the dimensions of these spaces are. Right? How do I get, for example, things at level 3? It's the number of partitions of 3, because I did 3, 2, 1 and 1 cubed. Then I will do, whatever, the next level, 4, 3, 3, 3, 1, 2, 2, etc. So the fellows at level D have dimension exactly partitions of D. Okay? So this representation of the Heisenberg algebra has this property that the fellows at the grade D guys have dimension exactly P of T. Okay. Now, how does that prove what we want? We wanted to prove that the Heisenberg algebra acts irreducibly on Fm. Okay. So recall that Fm has that same dimension property, that its different graded pieces have dimension exactly PD. So inside Fm, so here's a model of Fm, if you wish, sorry, upside down now. This is psi m. These are the different energy levels of, so this guy is Fm ka first degree piece, Fm ka second degree piece, and so on. Right? First degree piece means energy 1 more than ground state. This is energy 2 more than ground state, and so on. So I've just written out a model of Fm. You know what the size are, what they look like, right? You can index them by partitions whose things add up to 1, 2, 3, and so on. Now inside this space, I want to know how, I want to claim it's invariant under the Heisenberg algebra. So let's do the following. Let's just take this highest weight vector and just act it by the Heisenberg algebra. Let's generate a submodule. Okay. Just generate the submodule by hitting this psi m repeatedly by the Heisenberg.
Already know it's invariant under Or under where is this Heisenberg? Under A infinity.
No, that's what I'm proving. That's what I'm proving by sort of looking at the Heisenberg algebra. I'm claiming that it's invariant it's irreducible under the Heisenberg algebra.
Yeah, but we know it's invariant already.
It's invariant is known. Yeah, sorry. Yeah. It's a but H is a subalgebra, right? See, so I take H and I hit it on the highest weight vector. In general, only it'll generate some subspace of this, right? Because H is after only a subalgebra of A infinity. So I hit it and then it will generate some subspace. But the point is that this subspace, uska dimensions at each level actually are equal to the ambient dimensions. Why? Because this guy is a representation of the Heisenberg algebra, and there's only one representation possible really. Okay, which is the one whose dimensions are those. Okay, I mean only one irreducible representation possible, which is the one whose dimensions are PD. So it actually matches up with the ambient dimension. No, at each level it matches the ambient. So there's no other way out. It has to actually give you everything. Okay, so what this says is that, so what we have proved finally is that the Heisenberg algebra, which you get from the shift operators, that acts irreducibly on this space.
What's the isomorphism between these?
Between which? Which two?
These are the same isomorphic, right?
Yes.
Bosonic and
Yes, that's called the boson fermion correspondence. I still don't know what that is. I have to figure that out next. Yeah. Sorry, what? Why is this? No, so what I'm saying is, see, if you try to ask what do irreducible representations of the Heisenberg, the infinite Heisenberg algebra look like, the answer is that you can only get, there's really only one. Any of them is isomorphic to S of H minus. You're right. Yeah, yeah, exactly. I should say I'm in this highest weight. Yeah, I'm looking at highest weight irreducibles. Oh, you're worried about the more general irreducible. Yeah. Sorry, I have no idea what they are. Yes. What? Illa, among the. Correct. Yeah, that is too much. Yeah, I don't mean that. Yes. Yeah, in the highest weight category, I'm looking at all guys which will admit. Yeah, I have to. Yeah, I don't know what the precise.
So category O
for the Heisenberg.
The Heisenberg algebra corresponding to the Cartan plus the imaginary groups.
Right.
There I told we can define the moment.
Huh.
Define the category O and the moment.
Okay.
Similarly, you can do it
Here again. So if you have a Heisenberg algebra, you can define this category O, for example. So it's sort of like highest weight representations and the direct sums and so on. In that category, the irreducibles are all of this form. I mean, there is only one. Only one irreducible Heisenberg. Right, yeah, exactly, correct. So all that formal stuff will work the same way, but one has to be careful that you just have to say that it only works here.
seems like it should be related to the duality between elementary and complete symmetric.
Which one? This boson fermion correspondence involves the Schur function and so on. So it will have things like that. Schur functions, H's, E, everything comes up. Yeah, absolutely. Yeah.
Pure count.
Right, yeah. I mean, it's amazing that something like this can. Okay, so why are we interested in this? Because finally that what I have shown is something stronger than what I set out to prove, that this is actually invariant, in fact, under the under H and irreducible under H. And so the last thing I will say is that you can actually realize the affine SLN, or in fact affine GLN inside this. So let me just tell you how that's done. So the claim is the following, that recall these GLN hat or SLN hat So maybe SLN hat is somewhat more familiar. Recall this affine algebra that Venkatesh defined. The claim is that this guy can actually be, put inside A infinity. So before that, let me recall SLN hat was actually constructed in a few steps. First, you had the loop algebra, right? SLN T inverse, which is SLN C tensor C T inverse, right? You first construct a loop algebra of these guys. Now that thing you can also do for GLN. There is no harm. You can take all n cross n matrices in which all the entries come from T inverse. Okay, this is called the loop algebra of GLN. So the point is that the loop algebra of GLN naturally sits inside A infinity, A bar infinity. Okay, so this is sort of where I'll start next time. So let me tell you where we are going. So GLN TT inverse actually sits inside A bar infinity. You can realize it as infinite matrices. Okay, that's one. Now having done that, the central extension of this guy, which again is defined analogously to the case of SLN. So there is a central extension given by a cocycle. The cocycle has the same formula. You just say it's k times delta whatever m minus n trace of xy, and this guy will turn out, because remember this guy is centrally extended from here. Okay, so it sort of seems reasonable to expect that this central extension will turn out to embed correctly, meaning the cocycle formulas should match correctly when you go down. Okay, so I will be able to embed this inside this, and then of course the D is not a very big deal. That's just like a grading operator which you can throw in later on. So this is almost the affine algebra if you wish. So this is what we might have liked to call GLN tilde, one step short of the affine. This guy is actually embedded inside A infinity, and the key property is that this actually contains this Heisenberg algebra that I talked about. Okay, and this Heisenberg algebra sitting inside GLN hat is what's called the principal Heisenberg algebra. This is a very important Heisenberg algebra. It's not the Heisenberg algebra that Venkatesh talked about, which is usually called the homogeneous Heisenberg algebra. What you start with the Cartan and the imaginary root spaces. This is somewhat different, but this guy turns out to be contained in all the GLN tildes. Okay, and so irreducibility of this now acts on the fermionic Fock space. Irreducibility of this under H means it's of course irreducible under GLN tilde as well as A infinity and so on. Okay, and it will turn out that this, I mean not just F but each FM is reducible. It will turn out that this F0 is actually a copy of the representation we are looking at. Okay, so this is the reason for wanting to do all this. This is some irreducible highest weight representation. So I have to qualify it a little bit, because this is not GLN but rather SLN. So I have to do a little bit. It's not quite right as stated, that I have to take F0, take the highest weight vector and only see what happens when I have to restrict everything to SLI. Okay, so this under plus with some restrictions, so with some little bit extra restricting to SLN hat. Okay, so that will give me some submodules, not F0, something slightly smaller than F0. What you get by starting with the highest weight vector of F0 and acting only by SLN hats, that bit is actually a copy of V lambda naught.
So that restriction will again be irreducible?
Yes, that restriction will be irreducible, absolutely. And that will be this irreducible representation V lambda naught. So this is a fermionic model, if you wish, of V lambda naught. Okay, where you can sort of think of, since F0 is sort of like parameterized by partitions, right? So some of those partitions will turn out to parameterize, even bases, if you wish, of V lambda naught. We'll eventually only be worried about crystals. So where what I'm going to do in the last two lectures is to say, so I might not really end up giving all proofs of this, but hopefully I'll at least say enough to convince you that this is plausible, and then just describe the crystal structure of V lambda naught in terms of partitions. Okay, in terms of the sorts of things which index basis of F0. Okay, which is all partitions, and these operators. So remember, I talked about LS paths for V lambda naught already, but I didn't mention E's and F's. We didn't actually analyze how E0 and E1 act, or F0 and F1. Okay, so that's still missing from the SL2 hat. So I'll come back here to the SL2 hat picture in this new way of doing it, and then tell you how the E's and F's act. That's the key combinatorial thing we look at. Where does N play a role? M, you mean? SLN hat. Yeah, that will come up in the next. No, F0. No, this is V lambda naught for SLN hat. Yeah. No, that's what. So I'm restricting, right? See, I'm taking this F, so that's sort of what I said. So it's not F0 really, something slightly smaller than F0. There is a sub of F0 which I should look at here. So F0, I don't know, you see F0 has this psi 0, that vacuum vector. I need to only act on it by SLN hat. Whatever I get by acting SLN hat on that guy, that is a sub of F0. And this subspace is isomorphic to V lambda naught. Which is not irreducible? Yes, it will change with n, yeah. No, but this subspace itself is changing with n. Yeah, not the entire F0, just this. There is a certain subspace of F0 which will turn out to give you the V lambda naught. Yeah, but yeah, okay. Which one? Huh. Yes, yeah, that's the embedding, that's how it's embedded. Yes, it's there for all, yes, it's there for all. Huh? No. You are only looking at. See, but this subspace is changing, it's not the same subspace. See, this F0 is the same, F0 is constant. But then this subspace is different now. Each time it's a different subspace, no? Yeah. Heisenberg inside GLN hat. The embedding of GLN hat. No, not for SLN hat. Not SLN hat, no. That will not sit inside SLN hat. That Heisenberg will only be inside GLN hat.
So that will correspond to the diagonal bands, identity, length of CP.
Correct. Yeah, in some sense. Yes. Yeah.
Then, if I take GLN hat in the model generated by Sina, it will be full.
Yes, correct.
Because we are ignoring the identity.
Yes, correct. Yeah. Then it gives you just the SLN. Yeah. Yeah. No, I'm still very confused by a lot of this actually. But hopefully it will be clear. This all of this is from Katz and Reina's book, by the way. So I should have said that right in the beginning. So reference for all this is Katz and Reinhardt's called Bombay Lectures on Highest Weight Representations. Yeah.